Okay, so let's now generalize the sum rule. So this more general version of the sum rule is sometimes called the principle of inclusion-exclusion. Okay, big words. Basically what it means is how to compute, the number of objects when, previously we said that if you have n objects and there are n1 of type 1 and n2 of type 2, okay, then the total number of objects n is equal to n1 plus n2. Okay, so sum rule, so inclusion, exclusion. So you have two sets of objects, and there's n1 here, n2, and so the total number n is n1 plus n2. Okay, and that relies on the fact, that each object is either n1 or it's n2, but it cannot be both types. Okay, so it's sort of like you're one of those types. Okay, and then I can count up type 1, count up type 2, add them together, I get the total number of objects. Okay, the situation is different if the types can overlap. Okay, so let's look at two overlapping sets. Okay, so basically this says that the union A1 union A2, when they're disjoint, is equal to the sum of the two sizes. Okay. Now things get complicated if these two sets can overlap, and the number of biology books are 500, and the number of statistics books are 300. So how many books in all? Well, we might think it's 500 plus 300, but in that example, you've got biology books, okay, and you've got statistics books. And you have some biostatistics books. Okay, so there's overlap. So you cannot just add. So let's see what's the size of this union. So this union is made up of three regions. And now let me color code these three regions. So there's the biology books, which I'm going to color code with, black. And then there's the, statistics books. Let me color code those blue. There's this region. Okay, so think of this as biology only, statistics only, and then there are the joint books, the biostatistics books. Okay, so let's color this region red. Now, we're interested in the size of this whole region, the size of the union, or the number of elements in the union. Okay, so the union, union is equal to black plus red plus blue. Now that I can do because look, the black, the red, and the blue are disjoint regions. So I can apply the sum rule to black, red, and blue. Okay. But we can say biology is equal to black plus red. And statistics is equal to blue plus red. Okay, now I would like to take, and we know that the number of books in biology is 500, and the number of books in statistics is 300. Okay, and I would like to take the sum of these. So bio plus stat, so bio plus statistic is black plus red, so is black plus red plus blue plus red. So black plus red plus blue plus red. Okay, and if we compare that to the size of the union, we see that the union is black plus red plus blue, black plus red plus blue. So I have an extra red in here when I just add bio and statistics. Okay, so I have to subtract the red. And that'll get rid of this red, and now I have black plus red plus blue, which is indeed the size of the union. Okay, now let me write that in a more general setting where, we can think of this set as A, this set as B, and we're interested in the union or A1, A2. So we're interested in the union of A1 union A2. Okay, and I want A1. So this is bio plus A2. So this is size of A1 plus the size of A2. But now that adds the red region twice, so I need to subtract the red region. But what is the red region? The red region is just the intersection minus A1 intersection A2. So, as stated, the problem cannot be solved. How many books in all? I would like to take 500 plus 300, which is 800. But now I need to subtract the red region once. So I need to know how many books are in both bio and statistics. I need to know the number of biostat books. Okay. Actually, this is a special case of this, where the intersection is 0. So this is more general. Now you might think, well, this was nice and convenient for using the counting, for using the sum rule for counting, because if I can count n1 objects in set 1 and n2 objects in set 2, then I can just add. So basically the sum rule allows us to simplify the counting of a complex object by breaking it down into simpler types and counting each type. And this is similar in spirit. It allows us to count the complex objects, which is this whole set, by breaking it down into 3 types of sets. These sets, those which are only biology, those which are biology, those which are statistics, but now I also need to count one more set, which is those which are both biology and statistics. Okay? And you might ask, why is that any easier than counting those which are biology or statistics? So this is biology or statistics, biology and statistics. Often it's easier to count the intersection than it is to count the or. And so that's why this is useful, because count the first type, count the second type, and then count those that are both types. Okay? So let's do an example. Example. How many numbers in the range from 1, 2, 3 up to 100 are divisible by 2 or divisible by 5? Okay? So, the way we can approach this kind of a problem is to define 2 sets. Let me define the set A2. A2 equals numbers divisible by 2. Okay? So those are just the multiples of 2. So those are the multiples of 2, which is 2, 4, 6, 8, and so on, up to 100. Okay? And we can see that this is exactly, the size of this set is exactly 100 divided by 2. So the multiples of 2 occur every second number. Okay? So it's 100 divided by 2. If I wanted to be more technically correct, I should take the floor. I should round down. Okay, I should round down. Because if I wanted the number of multiples of 2 in the range from 1 to 101, I would do 101 divided by 2, but that sounds like 50.5. No, it's 50. So I should round down. Okay? And I can define A5, which is equal to the multiples of 5, the number of multiples of 5, which is just going to be 100 divided by 5, rounded down, which is 20. Okay? And so I would think that your divisible by 2 or your divisible by 5 might be the sum of these. So this is 50. Okay? So divisible by 2 or divisible by 5 equals, the sum 50 plus 20, except that I would be wrong because there is an intersection. A2 intersection A5 is the numbers divisible by 2 and 5. Okay? So if you're divisible by 2 and 5, it means that you're divisible by the least common multiple of 2 and 5. Okay? So this is, 100 divided by the LCM of 2 and 5. Okay? The least common multiple. If a number is divisible by both 2 and 5, if and only if it is divisible by the least common multiple, okay, of 2 and 5. And the least common multiple of 2 and 5 is 10. So this is equal to, 100 divided by 10. I take the floor. I round down. Round it down, which is 10. So I have to subtract the 10. Okay? So minus the intersection. Okay? Minus the intersection. 10. Okay. Let's do another example. Okay. Passwords. So remember we talked about counting passwords. There are the 26. There are 26 lowercase characters, 26 upper, 10 digits, and 10 special. and the password has length 8. So password is equal to W1, W2, W3, W8. Okay. And nowadays it's getting even more complicated. So, well, first of all, this gives a total of 72 possible characters, 72 choices for a character. And if you have 8 characters in the password, you can sample, you can repeat characters. So the number of possible passwords, is equal to 72 to the 8. Okay. Now, it's getting complicated. Nowadays, they want you to have both an uppercase letter and a special character. Okay. So, valid passwords. So valid means you have an uppercase letter and a lowercase. And a special. Okay. So let's define the set of passwords that do not have an uppercase letter. So let's call this A sub U is, do not have uppercase. Okay. And A sub S, so the specials, so A sub S is the set of passwords that do not have a special. Okay. Then the invalid passwords do not have an uppercase or do not have a special. So invalid. So the invalid passwords are the ones in AU union A sub S. AU union AS. They do not have uppercase or they do not have a special character. So let's compute the number of invalid passwords. Okay. So the number of invalid passwords is equal to the size of AU plus the size of AS minus the size of the intersection. AU intersection AS. And this is an example where counting the intersection is much easier than counting the union. Okay, so the size of this guy is the size of this guy, which is the size of AU plus the size of A sub S minus the intersection. Now, if it doesn't have an uppercase letter, it means it's using 46 of these digits. These 26 plus these 20, so 46. And so you can construct any password you want of length 8 with just 46 choices for each character. So this guy here is 46 to the 8. If it doesn't have a special, it's using all the characters but these 10, so there are 62 choices for each character. So plus 62 raised to the power 8. And now we have to subtract the intersection. So if it doesn't have an uppercase and it doesn't have a special, it means you're not using the uppercase or the specials. Okay, so you're using just the digits and the lowercase in your password. So that's 36 choices for your password of size 8. So you have to subtract 36 to the power 8. Okay, so that's the number of invalid passwords. And why is that useful? That's useful because we have the sum rule that the total number of passwords, is equal to the valid plus the invalid. Okay, and so this here is 72 to the 8 is equal to the valid plus the invalid, which is 46 to the 8 plus 62 to the 8 minus 36 to the 8. Okay, so the number of valid passwords, is equal to 72 to the 8, okay, minus 62 to the 8 minus 46 to the 8 plus 36 to the 8. Okay. So nowadays, it's getting more complicated. They require uppercase and special, and so the number of valid passwords has dropped compared to if you only required a special. Okay. And you can go and compute this number. Straightforward application. Well, not straightforward, but an application of the size of a union of overlapping sets. Okay. Now, let's erase and talk about what about if you have more than two sets? Okay, so what about the union of three sets? So let's generalize the union of two sets to the union of three sets. So we have three sets, A1, A2, A3, and we're interested in A1 union A2 union A3. So we're interested in the size of the union of three sets. Okay. Now, you could treat this as two sets, where one of the sets is A1 union A2, set 1, and this is the second set, set 2. Okay, so then you can use the union of two sets to write this out, and then, so you can expand this out with the union of two sets, then you can continue the expansion and continue the derivation, and ultimately you'll get a formula for the union of three sets. So I'm going to leave that as an exercise for you, and you can read the textbook, it's in the textbook. So I'm going to give a slightly different derivation, okay, where, what I will observe is I'll do the usual thing. I'll do what I thought I should do in the first place, which is add up the three sizes, okay, which is what I would start off by doing in a naive way. Okay, so it's the size of A1 plus the size of A2 plus the size of A3. Okay, but now, if you think about it, when I added A1, which means I added this intersection, for example, this intersection. I also added the other intersection, but let me focus on the blue intersection. When I added A2, I added that intersection again. So I've added that intersection twice. Okay, and when I added A1 and A3, when I added A1, I added this intersection. And then I added it again when I added A3, and similarly with this intersection. A2 adds it, A3 adds it. So each of these blue intersections has been added twice. So I need to subtract them at least once, okay, or once. So let me subtract A1 intersection A2, A1 intersection A2. I'll subtract A1 intersection A3, so that piece, A1 intersection A3, and I'm subtracting because I added those twice, and I'm subtracting A2 intersection A3. Okay, so I'm subtracting A2 intersection A3. Okay, but now, so that takes care of these blue regions have all been added in exactly once. So these outer regions have been added once from these guys, and now the blue regions have been added exactly once. And so now let's see what's going on with this red region. Okay. When I added A1, A2, and A3, I added the red region once each time. So I've added the red region in 3 times. Okay, and then when I subtracted this intersection and that intersection and that intersection, the 3 intersections, I subtracted the red region 3 times. So I added it 3 times, I subtracted it 3 times. But then it's not there at all. It needs to be there once. Okay, so I need to add it back. So I need to add back A1 intersection A2 intersection A3. Okay, and this formula, which you can derive, okay, more formally, I left it as an exercise, okay, is the formula for the inclusion-exclusion formula for the union of 3 sets. Okay. This pattern generalizes. So add the sets, then subtract the intersections, then add the 3rd intersection. If I had 4 sets, I would add the sets, subtract the 2-way intersection, add the 3-way intersections, and then subtract the 4-way intersection. Okay, and that's the general inclusion-exclusion formula for the sum of for the union, for the size of the union of n sets. Let me just state it, okay, just so that I have stated it, but you can see the details in the text. So, inclusion, exclusion for n sets, A1, A2, up to A sub n. Okay, so what you do is you consider all the k-way intersections. So here's the 1-way intersection, it's just the sets. 2-way intersections, 3-way intersections, and so on. So the size of A1, union A2, union AN. So the size of the union of n sets is, you consider all k-way intersections. Okay, and then you either add or subtract or add depending on what the value of k is. And add/subtract depending on k. So you start by adding the 1-way intersections, then you subtract the 2-way, then you add the 3-way, then you subtract the 4-way, and so on. So we can write this compactly as the sum from k equals 1 to n. Okay, so you start with the 1-way intersections, then the 2-way intersections, and so on. Okay, but because of this alternating sign, we need something like -1 to the k. Well, it's actually -1 to the k plus 1. Okay, So the one way you add, the two way you subtract, the three way you add, and so on, okay, of the sum of sizes of all k-way intersections. Okay, so you get the sizes of all the k-way intersections, the sizes of all the two-way intersections, and then you either add or subtract the sum of all the three-way intersections, and then you add or subtract depending on the sign of -1 to the k plus 1. Okay, so this is the general formula, but we'll work with the three sets for the moment. Okay, and let's do an example. Okay, so three ladies walk up to the coat check in a restaurant. Okay, so you have lady 1, lady 2, lady 3. Okay, and they have their coats. Let's call them coat 1, coat 2, coat 3. Okay, so they check in the coats, and then when they're leaving, they get back the coats. Okay, and we're interested in the situation where none of the ladies get back their correct coat. Okay, so an example of such a situation is for lady 1, I give coat 2. For lady 2, I give coat 3. Okay, for lady 3, I give coat 1. Okay, so this is an example of what we call a derangement. So, none of them get back their same coat. And you could imagine generalizing this problem to n ladies. And that's called a derangement among n objects. So, n objects started out in some order, and now I'm going to mix them up so that no object is in the same place that it was before. It's called a derangement, the opposite of an arrangement. Okay, so we're interested in the number of derangements. How many ways are there for all the ladies to get back the wrong coat? So all ladies get back the wrong coat. How many ways? Okay, we want to count derangements. Now, there's a build-up way to count the derangements, and you can see the text for that. Okay, I'm going to show you the inclusion-exclusion approach to counting the derangements. Okay, so let us define the number of ways in which lady 1 gets back their coat. So let us define A1 equals the number of, orderings where, equal to the orderings, let's call it the orderings where lady 1 gets her coat. Okay. And let me define A2 as the orderings where lady 2 gets her coat, and A3 as the orderings where lady 3 gets her coat. Okay. So in these orderings, lady 1 gets her coat. In these orderings, lady 2 gets her coat, and in these orderings, lady 3 gets her coat. Okay. And how many orderings in total? Orderings in total, well, the first coat can go to anyone. I mean, the lady 1 can get a coat in 3 ways, then lady 2 can get a coat in 2 ways after lady 1 has picked a coat, and then lady 3 gets the coat that remains. So there are 3 ways for lady 1 to get a coat, and once you fix lady 1's coat, there are 2 ways for lady 2, and then there's 1 way for lady 3. So, there are 3 times 2 times 1 ways in which you can assign the coats. Okay, so that's 6 ways. Or 3 factorial. 3 factorial. Okay. And, okay. The ways, the orderings in which at least someone gets their coat means that either lady 1 gets her coat, or lady 2, or lady 3. So A1 union A2 union A3. Okay, this is the orderings where someone gets her coat. Okay, so if we know the size of this, we can subtract it from 6, and we can get the number of ways in which no one gets their coat. Okay, so the size of A1 union A2 union A3 is equal to the size of A1 plus the size of A2 plus the size of A3, okay, minus the pairwise intersections, minus the size of A1 intersection A2 minus the size of A1 intersection A3 minus the size of A2 intersection A3. Okay, and then plus the size of A1 intersection A2 intersection A3. Okay, so that's the inclusion-exclusion formula for the union of three sets. Wow, man. Okay, what's the size of A1? So, lady 1 gets her coat. So now, lady 1 gets her coat. So this is C1. Okay, and then now there are two ways for lady 2 to get her coat. So there are two ways for lady 2 to get her coat, and then one way for lady 3 to get the remaining coat. So 2 times 1 is 2. So this is 2. And similarly, for the number of ways in which, because by symmetry, there's no difference between lady 1, 2, and 3. So the number of ways in which lady 2 gets her coat is also 2. So this is 2, and this is 2. Okay. Now, A1 and A2. If A1 and A2 get their coats, so C1, lady 1 gets coat C1, lady 2 gets coat C2. Well, that just leaves coat C3 for lady 3. So there's only one way in which A1 and A2 get their coat, one way. And similarly, there's only one way for A1 and A3, and there's only one way for A2 and A3. Okay. What about, A1 intersection A2 intersection A3? A1 intersection A2 intersection A3 means lady 1 gets her coat, lady 2 gets her coat, and lady 3 gets her coat. So that's this one ordering. So there's just one way to do this. So the final answer, 6 minus 3 plus 1, which is equal to 6 minus 3 plus 1 is 4. So there are 4 ways, okay, in which someone gets their coat. Okay. So the derangements, the ways in which no one gets their coat, so the derangements, so this is the number of ways in which no one gets their coat, is going to equal 6, the total number of ways to hand out the coat, 6, minus the number of ways in which someone gets their coat, minus 4, which is equal to 2. Bam! So there are 2 derangements when it comes to 3 objects. Let's see if we can figure them out. Well, so if it's a derangement, then, lady 1 must get either 2 or 3. So if lady 1 gets 2, then, lady 2 being a derangement lady 3 being a derangement cannot get coat 3, so must get coat 1, and that means that lady 2 must get coat 3. Okay. On the other hand, lady 1 could get coat 1, in which case, lady 1 could get coat 3. Lady 2 cannot get coat 2, so coat 2 must go here, and therefore that leaves coat 1 for lady 2. So C2, C3, C1, and C3, C1, C2 are the only 2 derangements, and that's what we got. Okay. So, inclusion-exclusion. I've now left, lots of time to talk about the pigeonhole principle. What a simple principle, okay? And, it's very powerful. It's just a beautiful principle, just both on the grounds of how simple it is and on the grounds of how many applications it has. Okay? And it's going to be a very powerful application for us when we study the theory of computing, when it comes time to build a digital computer, okay, using all the discrete math that we have learned. Okay, so let's talk about the pigeonhole. Let me erase. And before I talk about the pigeonhole, I want to introduce you to something called a non-constructive proof. So let's do the speed erase. Bam, bam, bam.